Okay, welcome back. This time we are going to talk about some nice examples of polynomials. So this whole theory of polynomials is the general theory is of course very nice, but what makes it especially nice is the existence of many examples with some very special properties and so on. Okay, so there are a very large number of examples of nice classes of polynomials. I am just going to talk about two of them just to give you a flavor of what's out there. So the first thing I will talk about are what are called Chebyshev polynomials. Sometimes called the Chebyshev polynomials of the first kind. There is also a second kind. Now where do these arise from? So to sort of better appreciate this, what one needs to recall is a little bit of identities from trigonometry. So here is one of them, the double angle formulas. So if you are trying to find cosine of 2 theta, then here is the well known formula for it. It is 2 cos squared theta minus 1. Now of course there is more. If you try to find cosine of 3 theta, so theta is some angle. This is, well, again a formula that is probably also rather well known, 4 cos cubed theta minus 3 cos theta. Similarly, cos of 4 theta, if you wish, can be computed from cos 2 theta by thinking of it as cos of 2 times 2 theta. So that is going to be, I guess, 2 cos square 2 theta minus 1, but I am also going to further write this out. Cos 2 theta is again some expression in terms of cos theta. So this is 2 times 2 cos squared theta minus 1 the whole squared minus a 1. Okay. So the point being that of course I could expand this out a little bit more. The final answer is going to be some expression which is a combination of powers of cos theta, okay, and so on. So you keep going. The key thing is that if you write cos of n theta for any n, 5 theta, 6 theta, 7 theta and so on, they can all be written as some polynomial in cos theta. Okay. So the key point here is let n be any natural number, then cosine of n theta is in fact some polynomial, can be written as a polynomial polynomial in cos theta. So observe, what we mean by that is the following: cosine of n theta can be written as some polynomial called Tn evaluated at cos theta. So Tn of x is some polynomial. In place of x you plug in cos theta, what you will get is exactly the value of cosine n theta. Okay, so let us see what do we mean here in our examples. If you put n equals 2, consider the polynomial T2 of x, which is 2x squared minus 1. Now if you plug in x equals cos theta, then that is going to give you 2 cos squared theta minus 1, which is exactly cosine of 2 theta. right. Similarly, you take the second polynomial that I wrote down there, 4x cubed minus 3x, you plug in x equals cos theta, it is 4 cos cubed minus 3 cos, and that is exactly cosine of 3 theta, right. So this is what we mean in general. There is a sequence of polynomials t0, t1, t2, t3, t4 and so on, such that in place of x you put cos theta, what you get is exactly the value of cosine n theta. Okay. So first let us see, why is this statement even true? Why is it true that cosine of n theta can be written as a polynomial in cos theta, and also simultaneously what these polynomials Tn look like. So to do this, so let us recall the identity for addition of angles. So I am going to write the following identity down. Let us look at cosine of n plus 1 theta. Okay, so that is just cosine of n theta plus theta. So it is like cos of a plus b. So the addition formula says it is cos of a times cos of b minus sine of a sine of b and what we will do with this is the following. So just a small trick to manipulate this. So let us add and subtract a cos n theta cos theta, the first term. So I will do the following, I will rewrite the first term, I will add another copy of the first term and subtract out what I have added. Okay, so what does this manipulation give us? Well, if you observe what it does to the last two terms now. So this is cos of n theta cos theta, and this becomes minus of cos n theta cos theta plus sin n theta sin theta. Okay, so let me just do it right here. So this is a minus and that is a minus, so I can put them together with a plus, but that is again the identity, but now for the difference of the angles. So that is now cos of a minus b, so this becomes minus cos of n theta minus theta, so that is n minus 1 theta. Okay, so what does this tell you? Well, it says that if you look at this polynomial t n plus 1x, so let us just let us look at the left hand side. If we grant that it is a polynomial t n plus 1 evaluated at cos theta, that is the left hand side. The right hand side is, well, what is it? Again I am going to write cos n theta as a polynomial in cos theta, so that is 2 times Tn evaluated at cos theta times cos theta minus, what is this again, cos of n minus 1 theta, so this is just Tn minus 1 evaluated at cos theta. Okay, so all I am doing is, so for the moment just take this for granted that cos of n theta can be written as some polynomial evaluated at cos theta. I am trying to find out what property those polynomials satisfy. Because we have this identity and because of all these manipulations, this polynomial t n plus 1 must be equal to 2 times Tn of cos theta times cos theta minus Tn minus 1 evaluated at cos theta. Okay, so these two things are in fact the same. So what does this tell you about? So observe that we have really plugged in cos theta in place of x, so replace all the cos thetas by x's. In other words, it says that this polynomial t n plus 1 evaluated at x is in fact 2x, so the cos theta here is an x, minus t n minus 1 of x. And this is valid for what values of n? Well, here I need at least n equals 1 in order for all this to make sense, because I am sort of looking at least cos of 0 over here. Okay, so t n plus 1 of x is just 2x t n x minus t n minus 1 x. This is valid for all n at least 1. Okay, so in fact these polynomials t n's that we are trying to understand here are given by this very simple formula here. Now this is not quite like a usual formula, this is what is called a recurrence relation. So we would call typically a thing like this a recurrence. Because it gives you a formula for Tn plus 1 in terms of lower Tn's, in terms of Tn and Tn minus 1. It does not give an explicit formula for the Tn itself, right, but just in terms of the lower Tn's. But that is still quite a valuable piece of information because it allows us to quickly compute the first few values. So observe, so let us just use that to write out this table here. So observe what are these, well, I should also have written the earlier polynomials. So here I have written T2, (4x cube minus 2x). So observe, in fact we also know what T1 and T0 are. T1 is just, T1 is supposed to be what? If you plug in cos theta as a polynomial in cos theta, right. So that is just the polynomial x itself. So T1 of x is just x. T0 of x is, I plug in place of n I plug in a 0, so it is cos of 0, that is just the constant 1. So in fact T0 of x is the constant polynomial 1, T1 of x is the polynomial x, the next guy is 2x squared minus 1, 4x cubed minus 2x and so on. So now let us just calculate, say maybe okay, let us just see whether this recurrence relation actually holds true. So what does the recurrence relation say? T2, we should already be able to figure out T2 from there. So remember this is the recurrence relation, Tn plus 1 of x is 2x Tnx minus Tn minus 1x. So I will plug in n equals 0 here, or rather n equals 1 here. I will get that T2 of x is 2x T1 of x minus T0 of x. Okay, so let's do it there. So T2 should actually have been 2x times T1 minus T0, and this is what, 2x times x minus T0, so 1. That is exactly 2x squared minus 1. Let us compute T3 in a similar fashion. T3 according to the recurrence relation should have been 2x times T2 of x minus T1 of x. Okay, so let us use this to calculate. It is 2x times T2 of x is 2x squared minus 1, T1 of x is x, so that should be 4x cubed minus 2x minus x, which is minus 3x. Right. So observe that the well known values of T2 and T3 can actually be obtained in terms of the preceding values by using the recurrence relation. So similarly if you did T4, it would just be, you take 4x cubed minus 3x, you multiply it by a 2x and you subtract out the previous term. So T4 should actually be 2x times T3 minus T2. Okay, and of course one can just work that out in full, see if it matches up with the thing that we already had. Okay, so that is these polynomials here are what are called the Chebyshev polynomials. So Chebyshev, so Chebyshev. These polynomials for n equal to 0, 1, 2, 3, it is really a sequence of polynomials. Now what are the main properties that we have sort of encountered so far? Well, the first thing is that they satisfy a recurrence relation. That's one of its most important properties. T0 is 1, T1 is x, and all higher values, and if you wanted to know what Tn plus 1 was, you could get it in terms of the two preceding values of t. So you multiply Tn by 2x and you subtract Tn minus 1. This is for all n at least 1. In other words, T2, T3 and so on are the ones for which you can apply this reconciliation. So that is the first property that they are given by a reconciliation. The second interesting property is sort of obvious when you look at the table. They are the first few polynomials are 1x, 2x squared minus 1, 4x cubed minus 2x and so on. In fact, the degrees of these polynomials sort of grow by 1 at each step. So in general, T0 is of degree 0, T1 is of degree 1 and so on, Tn is of degree n. Okay. In fact, further, if you sort of look at the table again, you will notice that Tn of x looks like the following. It is some multiple of x power n plus of course lower powers of x plus plus linear combinations of lower powers, but this leading coefficient, the coefficient of x power n is in fact a power of 2. It is 2 power n minus 1. Okay. So here for instance I have 2 power 1, this guy is 2 squared, this is 2 cubed and so on. So this is true for, let us see, what values of n? At least 1. It looks like this for n at least 1. Okay. So even the leading power is very easy to determine in this case. And what are the other properties that one notices from just the table is that Tn of x only contains, so for instance T2 only has x squared and the constant term, it does not have an x term. Similarly, T3 has x cubed and x, it does not contain x squared or a constant. In other words, if you take Tn and if n is even, it will only contain even powers of x, and if n is odd, it only contains odd powers of x. Okay. So I am sort of stating various interesting properties without proof really, but each of them can be proved rather easily. So let us see, Tn of x is only has even powers of x if n is even, and similarly only has odd powers of x if n is odd. Okay. So it has that very nice property. Now here's the rather interesting property of the Chebyshev polynomials. So they have a really interesting behavior under composition. So notice that I mentioned in one of the earlier lectures that here is an operation you can perform on polynomials. You take f and g, two polynomials, you compose them, you compute f of g of x. What you get is another polynomial whose degree is the product of the degrees, right. But the thing with the Chebyshev polynomials is, if you take the Chebyshev polynomial Tn and you compose it with the Chebyshev polynomial Tm. Okay, so this is a degree n polynomial which you are sort of composing with a degree m polynomial. So what are n and m here? So they are just greater than or equal to 0. What this gives you is, well, in general it is a polynomial of degree n times m, right. So that is the best you can say, but in fact it turns out to be the Chebyshev polynomial itself of degree nm. Okay. So it is rather interesting that when you compose two Chebyshev polynomials, the answer is again a Chebyshev polynomial. Okay. And so let us just prove this, because the proof is actually very easy and just a direct consequence of the trigonometric definition. So observe that on the right hand side, so let us calculate what is T and m of, instead of x I will put cos theta, so that it leads back to the definition. If I plug in x equals cos theta on the right hand side, T n m of cos theta is by definition just whatever you get when you compute cos of nm theta. So you take cos of this multiple of theta, you write it in terms of cos theta, that is exactly this guy T n m of cos theta. But this thing here can actually be thought of as cos of n times m theta. And notice that in fact we did this initially when we were trying to compute cosine of 4 theta. We said 4 theta is 2 times 2 theta. So if you know the answer for cosine 2 theta, you can use that to do the next calculation. So this is similar. If you want to compute cosine of nm theta, it's cosine of n times m theta, and think of this as your new angle, m theta as your new angle. So it's like trying to find cosine of n times an angle, but that's again given by the Chebyshev polynomial. To find cosine of n times alpha, you just have to compute Tn of cosine alpha, where alpha now here is m theta. Okay, and of course again cosine of m theta by definition is just what you get when you plug in Tm of cos theta. Okay, so just this cosine of a multiple of theta, the definition is what sort of gives you this property, that Tnm evaluated at cos theta is the same as Tn of Tm of cos theta. Okay, and of course from that you conclude that these two things are really the same. Nm of x is the same as Tn of Tm of x. So that's really the proof of this composition property of Chebyshev polynomials. And here's the final property that I want to talk about. What are the roots of Tn? So if you want to figure out what the roots of this polynomial are, well, here's what you have to do. You must ask what are the values of x which will make Tn of x 0, right? So we are trying to ask, if I want to find x for which Tn of x is 0, what does that tell me about x? So as usual, let's plug in x equals cos theta. So that sort of gives us a natural handle on the problem. So if you think of x as cos theta, Tn of cos theta, let's compute it. It's just, well, we know by definition it's cosine of n theta. And so the question really becomes, for what values of cos theta would cos of n theta be 0? So to find a root, it's really the same as trying to solve this problem. We want to figure out values of theta for which cosine of n theta is 0. And of course that's a very easy problem, right? So we know exactly when cosine becomes 0. So what are the roots? These are exactly, so what are the values of theta? So we are now looking at, let's see, so the roots. So let me just write down the statement. So the roots of Tn of x are the following numbers: cosine of theta, where theta is basically of the form 2k minus 1 divided by 2k times pi. K is a number between 1 and n. So the claim is these are the values of x for which Tn of x would be 0. Okay. So let's see, if you plug in, let's just check that this is true. If you take x to be this value, so let's just check. Suppose I plug in, so what is Tn evaluated at this number, for instance? So you take k to be anything between 1 and n, and let's try to evaluate Tn at cos of this number. So again, by definition, this is nothing but this is 2n. So by definition, Tn of cos of something is just cos of n times that angle. So it's n times this angle, which is 2k minus 1 by 2n times pi. But now the n cancels the n. What this means is this is cosine of 2k minus 1, which is an odd number, times pi by 2, right? But cosine of an odd multiple of pi by 2, so it's either pi by 2, 3 pi by 2, 5 pi by 2 and so on, cosine of odd multiples of pi by 2 is exactly 0. So this is in fact 0. Okay? So each of these numbers, if you take x to be this number and evaluate Tn on this number, what you are guaranteed to get is in fact a 0. Okay? So here are the roots of the Chebyshev polynomials. So what that means is in fact the following, it implies the following fact, that you can actually since you know all the roots, remember we have done this again once before, if you know the roots you can factorize the polynomial. You can write Tn of x as, what is it, each of these roots will contribute a factor. So this is just product of x minus cosine of 2k minus 1 by 2n times pi. So it's x minus this, where k runs from 1 to n. So these are the n roots, n distinct roots of this polynomial Tn. So each of these will in fact be a factor of Tn. So we have this, but of course there could be a constant in front, right. So these will not capture the constant in front, but again remember that was one of the things I said, Tn of x looks like 2 to the n minus 1 times x power n. So this should really be, the constant in front is exactly the leading coefficient 2 to the n minus 1. Okay, so here's the final fact which you more or less can deduce from the knowledge of the roots. Okay, so this statement is true for n at least 1. Here's an explicit expression. Okay, and it's rather remarkable that this expression holds, because just looking at that sequence of polynomials, you know, whatever 2x square minus 1, 4x cube minus 3x and so on, it seems rather remarkable that when you factorize it, what you will get will be cosines of some strange angles. Okay, so it's a rather remarkable thing. So let me just end this by just observing, if you look at T4 of x, so just plugging in this formula, here's the example. If you take T4 of x, it's in fact 2 cubed, that's n minus 1, times x minus, what are we going to get, cosine of pi by 8, x minus cosine 3 pi by 8, 5 pi by 8 and 7 pi by 8. So that's the formula for T4 of x. And of course you can also explicitly compute it from that recurrence relation and so on, and you will get some strange formula for it, meaning some degree 4 polynomial, and it's rather remarkable that that polynomial actually factorizes in this way.